organized jointly by ACM India Council and ACM Special Interest Group on Computer Science Education's Indian counterpart, I6CSE chapter, on an interesting topic, a new CS curriculum for the smartphone generation. I am Chitra Babu, Chair of ACM India I6CSE chapter, also professor at the Department of Computer Science and Engineering at SSN College of Engineering, Chennai. And I would like to briefly tell you about the activities of ACM India and the I6CSE chapter. You can see ACM India at a glance on this slide. As an ACM member, you will be part of world's largest computing professional society. Out of the 1 lakh members worldwide, about 11% of them are from India and half of them are students. ACM India is spread across the country mainly due to its chapters. We have totally 20 professional chapters and 200 student chapters across the country. The chapters get access to ACM's Distinguished Speaker Program and also ACM India's Eminent Speaker Program. So you can invite any expert from these programs and ACM will take care of their travel. ACM India regularly organizes summer and winter schools for students in different emerging research areas in computer science for the past 3 years. Faculty for these schools are drawn from prominent academic institutes and industry. ACM has taken other education initiatives such as teaching partnership program through which faculty from eminent institutes or professionals from industry teach courses jointly with faculty in charge at the host institute. ACM also has taken research initiatives such as PhD clinic, where faculty and industry researchers who act as sounding board and provide useful suggestions to the PhD research scholars. We have something special for promoting gender diversity too. ACMW, which works for empowering women in computing, it has several initiatives for female students. It organizes Lady ADA programming competition, national level hackathon, grad cohort, a forum specifically meant for graduate students, and one of the summer schools exclusively meant for female students. ACM India has instituted 3 prestigious awards. One is Outstanding Contributions to Computing Education Award. The second one is Early Career Researcher Award, presented to individuals in their early career who have made outstanding contributions to computing while primarily working in India. The third award is for Outstanding Contributions in Computing by a Woman. This year's awardees will be receiving their awards at the ACM India annual event that is going to be organized at the Oriental Institute of Science and Technology at Bhopal in another 2 weeks. Now, I would like to tell a little bit about ACM I6CSE chapter. The primary objective of this chapter is to bring academicians and industry researchers together to discuss and disseminate research related to computing education and also best practices related to curriculum design, pedagogy, and assessment. Now, I would like to invite Prajesh Prasad of Flame University, Pune, to introduce today's speaker, Aamod Sane, and host his webinar by moderating the Q&A session at the end. Over to Prajesh.
Yeah, thank you, Chitra. So it is my pleasure to introduce Dr. Aamod Sane. So Aamod Sane received his PhD from the University of Illinois at Urbana-Champaign. His early research was in the development of software tools and distributed computing. And then he transitioned to industry to lead development in a software tools startup. And subsequently, he worked as a primary architect for e-commerce systems and then as the architect of web search crawlers and indexers, followed by work on semantic web and social sites. In creating various computing systems, he noticed that the most elegant solutions resulted from building a model of the underlying rules of the problem domain, much as scientists capture the key aspects of a problem in the form of mathematical models. So this observation led him to the study of the history of science and the origins of mathematics, especially calculus in the 1600s. And based on this study, he developed courses in mathematical modeling and then transitioned into academia. He then went on to found the computer science department at Flame University, Pune, where he is working on developing these ideas into a modern, intellectually captivating computer science program for students. And that is the topic for today's talk, computer science for the smartphone generation. So over to you, Aamod.
Yeah, hello all. Um, one second, let me share the screen here. Okay, so like Prajesh said, this is mostly a story of how, a kind of a justification for the computer science curriculum that we.
Sorry, Aamod, you're on mute.
Okay.
It got muted
Yeah.
in the middle.
Yeah. Hi all. So this is mostly this talk is largely a justification of the new computer science syllabus that we designed for Flame, together with some a pitch for what the future of CS is going to look like. So before that, I should tell you that I got this injury yesterday while chatting with some friend about computer science curriculum details. So I guess it dovetails with how much effort you have to put to get a curriculum going. Anyhow, that aside, let's see what the main points to discuss are. I'm going to tell you briefly about myself and my background and how is it that I came about to found a computer science department. Not something I ever thought. I mean, I thought in this day and age, all computer science departments are, done and dusted. They are already running, but turned out not to be. And so we got a chance to do something unusual. And so I'll run you through the process. So, okay. So I studied at Urbana-Champaign, where I got my PhD. And then
Aamod, sorry to
yes.
interrupt, but did you change the slide? We are just
I
seeing
changed the
first
slide.
No, we are just seeing the first title.
You have
slide.
not made it full screen.
I have. It's full screen.
It's full screen. Okay, but it's not going to the next slide. Okay, now it is coming. Yeah. Now
okay, so it's delayed a little bit. So I need to. Okay, that's what happened. Is it better now?
Yeah, now the second slide is visible about this.
Okay, yeah. So I studied at Urbana-Champaign, and after that I worked as an architect for search and semantic search at Yahoo, during which process I designed lots of new systems and algorithms and some new formal methods techniques for proving some of these systems correct. And or at least to the point where those of us working on it could believe that this was a reliable thing. And that's when I got interested in basically. I am using slide. Okay, somebody else is having.
It's not shared. Somebody is saying.
Wait. Yeah, let me see. I am using slideshow, but it's doing something weird. So let me just maybe restart this thing. PowerPoint is stuck in some strange thing. Okay. All right, that should be better. Yeah, please let me know if it's working fine. Okay, is that better now?
Aamod, they still can't see the slideshow. We can see the first slide, but it's not in the slideshow mode.
No, I think there is some delay on the network or something because.
Okay. So you're sharing your entire screen, right?
Yeah, I'm sharing my entire screen and it is full screen. So,
Okay. Okay.
okay, let me try something else. Maybe I'll just try a PDF
PDF. Yeah. Yeah. That might be better.
instead of PowerPoint. That's very strange. Okay, I'll just do this instead. Let's see how it goes. That's really funny because PowerPoint is normally not a problem. Okay, is that better?
Yes, Aamod. Yeah. Yeah.
Okay, yeah. So, so as I was saying, in doing these projects, I got interested in how maths is created. And so I stepped back from the industry a little bit to do some research on the history of calculus. After that, I taught maths for over 2 years to like a large assortment of students, ranging from 4th grade, 8th grade, JEE students, master students at a university, and so on. And then was offered this opportunity to start a new CS department. And I had not obviously done this previously. It's not like exactly a common thing to do. And I wasn't precisely a professional academic either. But I did have advice from people like Anuradha Lakshminarayanan and Jayaraman Valadi, and my like experience based on how people I hired in search, how they were performing, what did they know, should they know anything better, and so forth. So I was left with two strong impressions. One is that computer science is becoming increasingly mathematical day by day. It's not like the old days where your main job was to write some VB program or something and make it work. That lasted for a long while, but things are changing rapidly. And then the other impression I had was left from doing all these courses, that students who have grown up with these new facilities are fundamentally quite different from our days for sure, and their reactions are also different. So then I started thinking in terms of student generations, in terms of what is our audience, who is our customer, what are we going to talk about. So I divided that into three generations: the desktop generation, the laptop generation, and the smartphone generation. So the desktop generation is maybe slightly later than, say, people like me who worked on the old, CPM machines which booted up in BASIC. Whereas today's children, even when their desktops were mostly at school, their definition of what the software and what a computer is was different. Then there is the laptop generation where there are devices at home. And finally, there is the smartphone generation. Now, the thing about a smartphone is it's quite unique, so much so that this is an opinion from US Supreme Court Justice, that this is such a pervasive and insistent part of daily life that the proverbial visitor from Mars might conclude that smartphones were an important feature of human anatomy, right? So this is quite different, very different from the rest of us. For the desktop generation, apps and like Microsoft programs and games is largely the definition of computing, and some occasional glimpses of programming unless you happen to go into an engineering school. For the laptop generation, you had Microsoft plus much more sophisticated applications. And for those of us who got into programming, there was Linux and those kinds of things and open source and whatnot. But for the smartphone generation, the app is hardly distinguishable. It feels like the feature of a device. It's wildly sophisticated and pervasively networked. So communication and application are almost one and the same thing in practically every sense of the word. So the question is, how do you not bore such students? Because if your initial courses are asking them to do exercises like drawing stars on the screen and things like that, then what is the students' reaction going to be? Are they going to be happy with this kind of a thing? But does that mean that you should also build apps in the course? That seems like a overreaction in the other direction. So from knowing this wide range of students, I had formed some impression of what is it that students are really thirsting for, what makes them happy, what do they miss from their education, and how we might go around and give them some idea of what that is like. So my idea was that you shoot for intellectual seriousness, because despite what some people might think, my general impression of this wide range of students was what they miss is seriousness. They are either bored because their earlier schooling is rote, or it is not well justified, or it just becomes too tedious and seems irrelevant. So that is the thing you should not do. They are not, they are not easily taken in by necessarily all the smoothness and the jazz. You just have to get them interested in more of the behind the scenes things instead of the amount of flash that exists. So that is core to getting, anyway, that was my prejudice. And so far it seems to be borne out. So that's one side of the story. What is your customer like? What is your student like? The other side of the story is that most computer science syllabi have been designed long ago, and to be sure they have evolved, but there is something of an impression of the era in which the syllabus is actually born, which is still sitting around. And so I'll talk a little bit about that, and that is where, besides the observations about the nature of students, I will try to justify this impression of what the future of CS is going to look like. Now, one change in CS is pretty obvious to us all. It barely needs to be said. Linear algebra and statistics have become central in a way that certainly weren't when I or anybody else started to do CS. Feel free to ask questions. If there is a question in the middle, we can, depending on where we are, I'll happy to take them according to the place where we are. So one part of the change in CS is obvious. It hardly needs to be said. The most interesting thing is that the AI techniques are to modern scientific practice what calculus was to scientific practice in the 19th and the 20th centuries. So it's becoming an everyday tool. And the more something becomes an everyday tool, the greater the demand for it. Plus, there's little need to justify why this tool is needed. And so in this particular thing, we don't need to talk about so much. But there is one other change that is not well known, in my opinion, even by many CS people, that I want to talk about. Well, first, this one also we understand very well, which is the need for large-scale data processing software. Hadoop was the poster child, but that's getting packaged. Here, the crucial new ideas are the CAP theorem, which talks about the behavior of distributed systems, and related ideas which underlie many of the design decisions made in things like Hadoop. The core ones, there is, of course, incidental ones involving how to keep large-scale data and redundancy in disks and those kind of things, but those are not. But then here is one which is far less obvious. So main thing is that formal methods have come a long way. Formal methods have had a bad rap for a very, very long time for being boring, tedious things involving logic and all that. But towards the end of my time in the industry, these were already coming in, which is where I first encountered them. I was one of the early people to use these kinds of things. And so here there is an idea called model checking. And I will argue, I'll try to convince you that this changes the structure of CS and how we need to introduce it. So you can actually find job advertisements these days which ask for skills in things like something called TLA and Alloy. And here is one that Currently, there are no ads for, but there will be very, very soon, believe me. There is a tool called Lean, which is turning logic into a programming language. It is proving itself in mathematics departments, although it was built by computer scientists. And sooner or later, that will become commonplace, especially when it is mixed with things like ChatGPT. So that I'll talk a little bit about that as well. And then here is another thing, my remark about ChatGPT. See, basically, as programming tools get more sophisticated, people will be asked to focus on the purpose of programming. And so specification and its correctness, are you saying what you actually want to do, will start dominating. So algorithm design and conception will be in the hands of people, and more implementation will be done by machines. So we already see this happening. There are predictive programming tools from GitHub and similar. They're called AI assistants right now, but the assistants will graduate really, really quickly. So that's coming. And then ChatGPT itself will evolve to become a programmer to a large degree. And so the question will be, what dialogue do you hold with ChatGPT to make it do the right thing rather than how do you program? But to talk to ChatGPT at its level, you will have to actually understand programming quite deeply. So it's not like the human. I mean, so far there is no sign that the human is getting kicked out of the cycle, but certainly the role we play is going to change a lot. So these are the ones that we'll talk about a little bit. And here, lean and things like that have a role to play. So prediction. Formal automata used to be studied for the sake of compiler theory, but now the emphasis is going to shift for working on distributed programs. Now, in the past, a key reason was, things like parsing tools, and the next will be model checking. So for those of you who haven't seen this stuff before, or at least not in the form I will show you, I'm going to talk a little bit about what this means. So here is a description of a customer and a bank and their interactions, a store, a customer, and a bank, and it's talking about electronic payments. So you have a state machine which has these states, and then from the store's perspective, there is something like start, pay, redeem, transfer, etc., etc. Here you have a bank doing something similar, and here you have a customer doing something similar. Now, this is from a book which is not used, to my knowledge, as much as it ought to be. But I'll talk about what book it is shortly. And we are still teaching automata theory for old types of things. And then here is a detailed version, which involves some more analysis. And then what these guys do is they say, okay, if you want to understand the system as a whole, you have to take the product of all these automata and study their properties. So that's this slide. And it soon starts looking not so great. So this part is the tools used to analyze this kind of thing are called model checking. But here's the interesting part. This set of pictures is from a book by Hopcroft, Ullman, and Motwani in 2001. But the interesting thing is they don't actually pursue model checking, although the example they are using to motivate automata theory is this one. So that's my claim that this part of the world will change very, very fast and is coming. Okay, so claim number one. Claim number two, specification techniques. So you can already see that if you give students access to ChatGPT, all the basic assignments in CS, you can probably get ChatGPT to submit them. In the recent education conferences, there are already papers on, using ChatGPT for various things. But then here is something that we don't really know the boundaries of, and this is specification techniques. Because the question is that program properties are mathematical formulae. And if you learn to say it well, perhaps with the help of things like ChatGPT, then instead of writing, so this is about defining the purpose of programming. And my claim is that we'll start moving in that direction very, very fast. We may happen to do it in English perhaps, but the change is coming. And so there is this thing called Lean, which is a specific tool. For various accidental reasons, it became very successful in mathematics world. This is what Lean looks like. So they have made, so this is like a theorem that says that the sum of the first 10 natural numbers is, you know, n into n plus 1 upon 2 divided by 2, etc. So don't get too fixated on, you know, the looks if you're not familiar with it. Bottom line is, what used to be done on paper is being done on a machine. And then you can construct theorems from this. Now, it's not that CS people are going to do theorems necessarily, but the style of thinking like this will start having some effect. So that's the idea. And I'll tell you how we handle this in our course. So once you get used to it, and especially students get used to it, they will force us to like it. So that's my second claim. So therefore, with this background in mind, that if we are shooting for these changes, how do we design it? So our curriculum's first year is that we introduce significant ideas that lead to AI and formal methods early and build on them. The idea is that students get exposed to these things again and again, and eventually, presumably, they learn to think like this. So an example is there is a course called Introduction to Programming by Specification, which uses a functional programming language. It's quite like Lean, which I have showed you, and at some point we'll probably start using Lean instead of Gopher. But the point is that it's a functional language in which, at least for simple examples, there is little difference between a program and a specification. What the interesting thing is, student response to this stuff is great because they see programming in a direction which they simply haven't thought of, and they really like it. The second course that teaches something called computational modeling, which takes real world phenomena like compound interest, projectile motion, and shows how programs can describe these things. And in the second half, we teach elementary neural networks, because the core operation at the heart of a neural network is really trivial: averaging followed by nonlinear functions, etc., and maybe some little bit of feedback as needed. But simple tasks can be done, and so they at least get a hint that, okay, this isn't some horribly complicated thing we can only learn 3 years from now. This is quite a normal thing, and if anything, it's a mystery why such simple mathematics works. Right. And then lastly, there is a introduction to Internet of Things, which uses Arduino kit. So this way we set up like a appetizer for the kinds of things they are going to see in the future. So this is my claim: you shoot for intellectual seriousness. The first courses should convince students that there is far more to computing than languages and apps, which is what they have in their mind, because that's what they have seen in school, and then get them much more interested in the behind the scenes stuff. And our experience so far bears it out that they like this kind of thing. And in some sense, the stronger the student is, the more appreciation they have for it. Now, the rest of it, I will just describe some of the tracks. And in around, I think about, so this is 11:30 right now. So I have an hour. So we'll leave some time for questions, and we can talk about that. So the curriculum dependency, see, my goal is to introduce formal methods, and AI is of course there. And one other new thing we have done in the, well, new is probably wrong, but at least it is conceptualized differently than the other syllabi that I have seen. I would love to know if other people in the audience are doing things like this, and to what extent we overlap, because that would be really great. Okay, so this is the rest of our curriculum. That there is a formal methods track, and in this formal methods track, the way it's set up is, in the second year, the first course is mathematics for computer science. There is like a book with this name, and it basically teaches discrete structures in a fairly intense fashion. It's a book from some people at MIT. So that sets people up for the discrete structure side of it, which feeds into theory of computation. But theory of computation, the way we are doing it, is tilted towards the model checking thing, the product operations and those kinds of things. Not that we are not including Turing machines and all that, but the emphasis is shifted a little bit away from the classical methods and tied very closely with real life experiences. So for example, you can use a finite state machine to model a website, right? So that is one of the examples in the theory of computation course. So in that sense, the idea is not to leave theory of computation as a end of the cycle course to be studied by theoretically minded people, but do it early, because the idea is that in some sense, theory of computation is the unique selling point, as they say, of what computer science is. Once you absorb that, then you are ready to build. Of course, you have to pitch it properly at the second year level rather than anything too sophisticated. But that done, you kind of get across the idea that there is like abstraction is tractable. You don't really have to, be afraid of these abstract models. So for example, instead of asking them to just do automata on paper, we'll actually ask them to write automata in Python and get used to the idea that these formal models are not some arcane, terrifying thing. Now, these two then feed into the third year, which is applied formal methods. And applied formal methods is precisely TLA, alloy, lean, and those kinds of things that you can at least introduce to students. And so once you have these tools, you can do fundamentals of distributed systems and cloud infrastructure and DevOps much closer to the way we used to do it. So for example, you might not, I don't know if you know, there's something called Zookeeper, which is used in Hadoop. And the people who built Zookeeper built it together with a formal proof. And you can go get the formal proof, and it was done in TLA. So, and this is already like 2008 or something. So that's a long time ago. And so if that is done, then you can do this. It leaves some problems open. For example, can you find faculty who can teach this stuff and so on? So there is some cost to be borne. Right now, we don't have an issue with this, but I can imagine it being one. Now, the second one is the AI track, and the AI track is, I imagine it's traditional. I haven't looked too much, but linear algebra and statistics, and then you do, AI1 and AI2, as it were. If there was room, we would put another course, but there probably isn't. There is an optimization course available as an elective. So that's these two tracks. Now, the next track is something also, at least I believe, somewhat unusually configured compared to some of the others. And I will try to mention what is unusual. So this one is fine, right? It's a classical C++ course and a computer organization thing and architecture thing. So here you are taking more of a systems perspective, whereas here you are taking more of a details of chips and such perspective, but they are running in parallel. I mean, sorry, they are running one after another. So here you build up some fundamental notion of, like, here's a way to think about it. Every CS student who is using a device, including a smartphone, say, would know the details of that device. Right? How my machine works, because anyway you have one in front of you, you should master it thoroughly. And then you go into two of its details. So this one goes deeper into the CPU side of things. And this one is a course that I will talk about a little bit, systems programming, because I haven't seen this matter discussed, and Anuradha Lakshminarayanan, who used to work with us, suggested that this is an important thing, and it seemed right for us. And then the third year course, so this systems programming is basically a user's view of operating systems, And then this is the familiar internal kernel view of operating systems. So as far as I know, the user view is not emphasized as much as it should, because for us in the industry, this one is actually much more important in some ways than the classical inside out kernel perspective. And then this sequence provides background for these courses, which can build on top of that. So graphics, databases, and web systems. The web systems is also an unusual course. I'll talk about it a little bit. So here is one. So systems programming. So we look at details of the user interface of OSs. What are compilers, linkers, loaders? How is low-level memory management done? How do we implement data structures at this level? And not just data structures in memory, but also data structures on file systems, because we traditionally, data structures has been thought of as an in-memory thing. However, today's systems, especially things like Hadoop and all, if you look at what is important there, the in-memory representation is a relatively straightforward matter. It is the out-of-memory representation that is interesting. There are also strange tidbits in today's systems, which I don't know how many people have heard of, like linked lists say, right? It's fine that we teach them and we should teach them to everybody and all. But in practice, they are mostly just kind of like gym exercises involving pointers. You will find advice from lots of people and also experience in the industry that says that a linked list is like a seriously bad data structure, and you should not use it unless you are in hyper constrained circumstances for various reasons. So these are the kinds of things that the systems programming course gives you an opportunity to talk about. So I believe this is somewhat unusual. Here is one unusual course. The issue is that there is the traditional networking course and there is some kind of an apps course, but to my knowledge, the blended version is not available. So people's ideas of how the web works exactly and what the browser architecture is just does not exist. And so here, instead of a standalone course, we blend this with web systems, talk about HTTP and the more fancier versions of HTTP together with TCP, DNS, etc., and also discuss browser architecture, because increasingly the browser is the new operating system. So you really need to understand it well. And now the material is available. So people, in my opinion, could, I mean, I'm not saying necessarily replace operating systems by this, but maybe a future evolution should do that. Because browsers have damn close to operating systems inside them. So that's the other one. And then the rest of the courses, aside from the unusual things and the justifications, are, I think, relatively standard. So you have data structures, algorithms, those kinds of things. There is software architecture and engineering, one course in Sem 7, security in Sem 8, and some electives in semester 7 and 8, because this is that whole problem of a finite time available and you are trying to put in courses. So the applied formal methods course, by the way, this another one is about unusual courses instead of standard ones. Here we talk about SAT solvers and model checkers. Those are things that are discussed here. Okay, so that's about the structure we have. And what do I sort of am personally not too happy with? So one thing I didn't make a slide of, but I thought of to talk about was that despite talking about the smartphone generation and all that, we are unable to do a course on, or at least there's no room/expertise for a course on smartphones themselves. So there are, I think, things inside it that are quite interesting, because the design principles for smartphone operating systems are somewhat different from those of modern other operating systems. And perhaps it is the case that that modern OS books have started covering it. I don't know, but I know that from knowing people who built Android, that building that thing was not a simple thing. So presumably there is something to be said there, but I don't think people who know this stuff are available now, at least for now. And then there are some, constraints, like we have this major minor combination, 4 courses max. So one of the things we left out was compilers and languages as an elective. I love things like Prolog and APL and whatnot, but we're unable to do that. Could not find room for advanced algorithms. There is a mathematical optimization elective, and students can take it, but you can't require it necessarily. And then there is no standalone networks course, which misses on a few things, but I think we can live without it. So that's overall the idea. And as far as our experience is concerned, the first part of our discussion, which is these kinds of things, this type of course, the first year, that we have done several times. Our department is relatively new, so not much data is available exactly. But the response to this kind of thing has been very, very gratifying. So right, so that's as far as that we have. And I thought, depending on people's interests, I can go into the details of these things. So I didn't have anything necessarily pre-prepared, but if there is time available, then what we can talk about is a little bit more about what you need to do to build some expertise on things like formal methods and that side of the story, which is, like I said, relatively less explored. And also, what would you need to build something like systems programming? So if people happen not to have questions, then I can explain a little bit more here. But let's just first gather questions. We saw one so far.
Yeah, thanks, Aamod. Maybe we'll take some questions and then we can move to the other part. So Spruha is asking, so she would like to know more about how the curriculum is aligned to include smartphones for learning. So I'm guessing she's asking, how can they use smartphones in the classroom for learning? I guess that's what the question is.
I'd like some clarification. Maybe you can just speak out, Spruha.
Yeah, let me see if I can do that. Yes, Spruha, I think you can unmute and speak now.
Thank you, Prajesh. Yes, that's the same. My question is the same. Whether the curriculums for first year, second year, and onwards, do they also have some practicals or based on your smartphone? Because the formal methods seemed a little more towards theoretical oriented. So I would like to know how can we include smartphones for practical purpose as well, maybe.
So to the extent that we have thought about using smartphones as devices directly, has been about using them in student projects. So let me clarify a bunch of things. First of all, there is this course here. See, okay, what is unusual about smartphones? Let me first lay that out. What is unusual is people's apparent familiarity with it. Okay, what I mean by apparent is we use it every day, but much of the complexity is hidden from us, which is why I mentioned that, for example, the design principles of a smartphone OS are quite different from at the detailed level. Because, for instance, a smartphone OS has to prioritize an incoming phone call over absolutely everything. It has to do things like power management. Nowadays, even laptop OSs have started to do it, but the degree to which a smartphone OS has to do it is very high. That is one side of the story. The other side of the story is actually how those apps are built. Now, smartphones over the years have gone from being relatively thin devices to being thick devices in terms of being equivalent to earlier computers. But the one thing they do, which is very different, is that they cannot assume the network is on all the time. Okay, so the network here, you have to be ready for continuous disconnection, which is very different from other forms of software. So here, what happens is there is this web systems course, which can actually talk about that side of the story, because at a conceptual level, at least, browser application is no different from a smartphone application. There may be some details in how the windows are presented and so on and so forth, but the problems it has to tackle are very, very similar. And then except unless you have a game or something which is passively sending data, an individual game, then your app will be local to the smartphone, but otherwise even distributedness is an inherent part of it. So that's partly the answer, that the smartphone thing can be covered to some degree in the web setting, except you require people to use instead of the browser, you use them to build the toolkits that are available on this thing. There's a third thing I would like to answer regarding smartphones, and this is where I think student projects can do a better job, which is that smartphones also have a lot of interesting physical devices in them. They have, GPSs, they have direction detectors, they have cameras inside them. So in the long ago, when the iPhone was first introduced, one of the most unusual apps that arrived was from what's the name of that thing? There is some company in the Bay Area which has restaurant reviews. So that restaurant review company had this interesting property that you could stand in one place and turn your smartphone this way or that way, and it would show you the restaurant names in that direction. So that was quite remarkable. So those are the kinds of things that presumably a smartphone would allow you to do. But yeah, I mean, we haven't necessarily relied on because I'm not completely sure whether the limitations of those devices versus the time available in courses, etc., is easy to bridge. If you had faculty or external people who are mobile developers who can smoothen those kinds of things, then maybe something like that would be possible. So just to summarize, I said three things. One is, technically, smartphones are wonderful devices in details like operating systems and all. As programmatic devices, they give you access to cameras and things like that, which are not that readily available on, or at least are awkward on laptops. And thirdly, they share a lot of programming related concepts with web systems, so you can take care of that. Okay, so Spruha, does that help?
Yes, thank you so much.
Okay.
Thanks, Pruha, for the question. Thanks, Aamod. So Mrityunjay has a question about software engineering. So his question is, so how was the choice made that software engineering is not worth a track of its own? So it will be good to understand the perspective and the decision criteria on track selection, especially what to keep, what to drop.
Right, yes. Right. So like I said, the idea was that AI deserves a track on its own. I don't think any of us would disagree. Whether the unusual thing is to have formal methods. Now, the formal methods thing, my belief is that whichever students have a training in this thing will see a world that is simply inaccessible to others. I'm telling you, go look up ads for temporal logic of actions in Amazon and Google and whatnot. The kinds of people who can get hired for those, and the concern for that is spreading, by the way. These things are also important for understanding the foundations of, so something I didn't mention was, there is this programming language Rust, which we probably all have heard of, but the foundations of why Rust works are deeply dependent on theory of the kind I'm talking about. So there is this impression we have of theory being a somewhat disconnected thing on paper, and my whole point is that those days are behind us. The theory which used to seem arcane is very much not. So it's connected to this answer of Lakshmi's, but let me just first finish the software architecture story. So if you decide to keep these two tracks, what other things can you skip? That would be my answer to Mrutyunjay. That things like data structures and algorithms are, of course, unskippable. So is C++ and discrete maths. So now Mrutyunjay mentioned about a track. I mean, we are able to get one course in here, and technically I could argue that Alloy, which is one of these formal methods tools, is an aspect of software architecture, but never mind. What I would like clarification from Mrutyunjay, maybe you can write on the chat or something, that how could you have a track? What would the definition of track be here? So maybe while Mrutyunjay answers, I'll move over. Okay, so Chitra Babu said that.
So
sorry, go ahead.
Yeah, he's there.
Can you hear me?
Yeah, I can hear you.
Yeah, no, let me clarify that. So yeah, when I say software engineering track, I'm looking more from the perspective of, again, building. Hello, can you hear me?
Yeah.
So I'm looking more from the perspective of you build the capability around how do you take a system and work with it. You could build a new system, you can design a new system, and then again, if you look at the software engineering that is out there in the industry, requires multiple aspects, definitely requires formal, but then it requires other aspects of engineering, the manufacturing aspect of software, which doesn't get prioritized, and of course it doesn't get prioritized even today. So in a new curriculum like this, I mean, I'm just trying to look at, okay, why is it that you thought, okay, that can be taken care of maybe by formal method is what you're saying, but that is what I mean. You will put in many of these pieces, some of these pieces will come, but then there will be this manufacturing aspect of software, which I feel nobody looks at. And there are courses that will come in from systems, from formal, but then there will be aspects of really crafting a software.
Yeah, so we talked and we have talked before. So Prajesh taught the software engineering course as it happened this time, and we thought that instead of talking about abstract things like the agile process and this kind of thing, we would just teach them tools to make software. So there used to be a course called, or there is a course called basically something along the line, I forgot the exact name, but students at MIT and CMU by themselves have created a course called the Missing Semester. Okay, so the Missing Semester course teaches students about the tools used to build software, things like Git and all this. But I don't see our students yet of being the kind who can run a course like this on their own. So we decided to include some of what you are calling software manufacturing as part of the software engineering course. As to how to introduce things like processes and all, and aside from some lip service, my impression, and we'll study it and think about what to do about this later. My impression is students are too young and too inexperienced to understand what problems software engineering solves really, because they have never written large software. They have no idea what working in a real team with people leaving and joining and all that is involved. So I mean, right now we are using this very mechanistic definition of software engineering as a course that teaches techniques and maybe mentions things like processes and all, but not super in any great detail. So
Thanks. Yeah, no, I think that was good. Thanks for clarity.
okay, now Lakshmi says, I seem to be suggesting that we need to be getting students to create higher abstracted models. No, that's not what I'm saying at all. So the this formal methods is not like that. So let me give you an example. Let's say you are building, you are thinking of a web system that you want to design. Now, how many people would know, or how many people would think that the interaction paths of a web service or a web app involves a finite state machine? In my opinion, very few. Historically, you can actually find a book called Finite State Machines for Web Systems or something like that, for UI design or some such. So this is known in the industry, but it is completely not understood. What I'm saying is that abstract, you make real programs, but you think about them using abstract models, Lakshmi, because the idea that these abstract models are just some mumbo jumbo that mathematicians do is not actually correct. Maths doesn't work like that. It's meant to model real systems, and that is the sense that I'm trying to create.
So maybe Aamod, to just add to that, so you might have seen some students, or there might be students who have had no programming experience, right, in your courses. So how has their experience been like?
So they don't have any problem with it. First of all, the abstract models are introduced after the first year. And in the first year, they have already seen this multi-perspective view of programming. The first one is functional programming. The second one is imperative. The third one is hardware. So those are like multiple dimensions of programs that they have already seen. And functional programming in particular asks students to think of software symbolically, which is not something that imperative programming does, because imperative programming involves time and things like that, whereas functional programming doesn't. So it's kind of a little tricky to explain. It's easier to experience. But once you have written a functional program kind of thing inculcated in your head, then moving on to a more symbolic abstract thing is not so difficult. And functional programming has had a bad rap and not enough training on by faculty and all, so that they think it's a kind of programming. Not exactly, it's more of a kind of style of organized thinking. It's like an extension of school algebra to encompass programming. And by the way, if people are interested in these kinds of things, I'll be happy to hold talks for people who like this kind of thing, or at least would like to see more. And we can do them on a fairly, like maybe ACM can help, or do some summer schools or something. That will be fun, because the more faculty learn about these things, the easier it is to spread these ideas.
Yeah. Thanks, Aamod. We are running short of time, but maybe I'll just ask one final question since we don't have any other questions. So many of the faculty, they will be teaching standard Python or Java or C courses, right, in the first year. And your talk stressed upon the skill of improving student specification skills, right? So how do you think they can do it in their programming courses? What interventions do they need to do, or can they use? So how maybe they can use some prediction tools, LLMs. What are ways in which they can improve students' specification skills in standard courses?
Specification skills. It's a more of an example-driven thing. So what we will have to do probably, I'm just thinking off the fly. What we'll have to do is to just figure out what the a sufficiently large number of interesting examples is what we can think of, because if you have those, then you can spread them through various courses.
Okay, thank you, Aamod, for this interesting talk. Over to you, Professor.
Yeah, thank you, Professor Aamod Sane, for that very interesting thing. Some of the suggestions, I think we can take it up and that is incorporate in the next revision of curriculum, I guess, whoever joined today. So everyone can try their hands with these new ideas while you are revising the curriculum. And I also would like to urge everyone who joined today to become an ACM professional member if you are not one already. And also the membership to the I6 CSE chapter is completely free. So consider joining us to contribute towards improving the quality of CS education all over India. And we will also I'll try to talk to the